Yeah, good morning. In the last session I have talked about the cast structure, how to have a desirable cast structure, how to have a finite dendrites, how to have relatively wide equiax zone. These are important issues with respect to the cast quality. Now another important issue I will be discussing today, this is called the role of chemistry. That means the grade, whatever steel grade we are using, what effect does it have on the cast quality. This is very important. So we know that steel we can have different carbon, we can have different alloying elements. So for plain carbon and low alloy steels, the solidification will be dictated by how the solidification will take place, will dictated by, to some extent, to a large extent rather, by the iron carbon diagram. In iron carbon equilibrium diagram you have iron and carbon, but since in low alloy steels you have some alloying elements. So instead of carbon it is better to understand what is carbon equivalent. Carbon equivalent means how other alloying elements like common alloying elements like manganese, silicon, chromium, nickel, in what I am talking is, or molybdenum I am talking is a low alloy steel, how they affect the activity of carbon and how the iron carbon diagram gets influenced by that. Now there is another category of steel like stainless steel which has very high amount of chromium and nickel. Chromium is of course always there, minimum 11-12% chromium, maximum maybe 25-30, and nickel also might be there in most of the grades. So here the amount of alloying element is very high. So iron carbon diagram can no longer dictate how the solidification will take place in those grades. So iron carbon diagram or pseudo iron carbon diagram we call it can indicate how the solidification will take place in plain carbon and low alloy steels. But in stainless steel we have to go for some other diagrams that will come in afterwards when I discuss stainless steel. So solidification temperature range and the solidification sequence, that means what is the type of solid, is it delta or gamma, they are decided by the steel composition. When you are cooling a steel from liquid to the solid, I will come to the iron carbon diagram, it will be more clear then. What is important is to understand that depending on the carbon, it can come through the delta solidification or gamma solidification or something in between. So what are the possible routes? Let us try to see. First, the solidification sequence will depend on chemistry, also the solidification temperature range, because as you are going to more and more carbon or you are increasing the alloying elements, the liquidus and solidus they are changing. So the difference between liquidus and solidus, which is known as the solidification range, will also change depending on the chemistry. For 0.05% of carbon, solidification temperature is something, and when you go to 1% carbon, solidification range is quite big, and the actual temperatures of solidus and liquidus are also relatively lower. So what is important is, with chemistry solidification temperatures are changing, liquidus temperatures are changing, solidification temperature range is changing, solidification sequence is changing. So these are very important to remember. Now what are the possible routes when you change the steel composition? From liquid it can get into liquid plus delta region, then delta, and then finally to austenite. Or another route may be liquid, it is going to liquid plus delta, then peritectic reaction takes place. So liquid part of the liquid plus delta will generate gamma. So finally you are going to liquid plus delta gamma plus gamma region and then gamma austenite. Or when you are going beyond the peritectic reaction, what is happening? There is no delta. So liquid goes to liquid plus gamma and then gamma. Finally at low temperature you have only gamma, but the solidification mode is different. Please try to remember. You might tell at 900 degrees centigrade everything is gamma, irrespective of the chemistry, austenite. but that is half of the story. The half of the story, first we should remember that how the solidifying is taking place. Solidifying is taking place when the carbon is very low, you will find it is taking place to the delta region, and then finally gamma is forming. So, when within the peritectic range it is also taking place first delta and then going to gamma, but when this beyond the peritectic range, that means more than 0.5% carbon, it is only through gamma. The three possibilities are there. So, it is also important to understand when this delta to gamma transformation is taking place. Initially, as I am telling you, here delta to gamma. So, when this delta to gamma is taking place is important. That also has a lot of implications on the quality of steel, because that is a stress transformation stress from delta to gamma may add to the seriousness of the problem, quality issues. So, we have to remember that. So, how the transformation is taking place is important. Then now what is the mode of transformation, that is first important during solidifying, and then delta to gamma, that means this is also solid, this is also solid. This delta to gamma is taking place where? Is it during solidifying or after solidifying? That is important. As I have mentioned, if it occurs during solidifying, then what stage of solidifying? Is it at the early stage of solidifying or medium stage of solidifying, or towards the end of solidifying? That means at what range of solid fraction is taking place is important. All this will be more clear when I discuss the specific issues. And why this is important, how it is solidifying is taking place, because the strength of solid shell for delta and gamma are different. It has been found that delta ferrite is relatively soft, and austenite, I am talking about high temperature strength. This all solidifying means relatively high temperature properties are important. So, what is important is at high temperature what is the strength and toughness of solid shell delta or solid shell gamma. Gamma has much higher strength compared to delta. So, this is that is why how the solidifying takes place will lead us to what is the strength of the shell, whether it is delta or gamma. If it is delta, then it is soft, solid shell is soft. If it is gamma, solid shell is relatively hard. So, this is the first thing to remember. Now, let us come to the well known iron carbon diagram. So, let us look at the high temperature portion of the iron carbon diagram. This is the iron carbon diagram at the high temperature portion. That means, from liquid during solidifying, what are the phases you can make out from this high temperature region. This is the peritectic temperature. It starts at 0.1% carbon, ends at 0.5% carbon, and peritectic composition is at 0.17% carbon. So, just try to see how solidifying takes place. Say if you have a carbon steel where the amount of carbon is 0.05. So, what is happening? During solidification, delta initially it is liquid, then you have delta plus liquid, and then solidification is complete, means in delta mode only. So, when the carbon is less than 0.1% carbon, that means less than the peritectic range, we have solidification through only delta. And finally, this delta will in the solid state will go to gamma. So, during solidification we have only delta, and only at lower temperature during cooling we have gamma, and delta to gamma is taking place relatively high, because the low carbon means liquid as solid as everything is relatively high. So, solidification is taking place through delta, and delta remains for quite some time depending on the carbon. As you have very low carbon, delta remains for quite it comes down to quite low temperature, then only it transforms to gamma. Here this is delta plus gamma, and this is finally gamma. And if the carbon concentration is more than 0.1, then what is happening? Initial solidification is through delta only. So, it is we are coming down here. That means above this temperature, say 1500 temperature, above the temperature of the peritectic temperature, we have only delta, and when we are reaching the peritectic temperature, delta plus liquid is generating gamma through the peritectic reaction. Delta plus liquid is gamma. This is the peritectic reaction. So, that means when we are in this region, that means 0.1 to 0.17 initially liquid, delta plus liquid, then we have here gamma plus delta plus gamma, and finally gamma. That means that the peritectic temperatures lower than the peritectic temperature, solidifying is complete at this point. Now, when you are in this carbon range, that means 0.17 to 0.5, what is happening? Initially again solidifying is through delta only. So, initially delta plus liquid, then at the peritectic temperature some of the delta and liquid is only transforming to gamma, and then below that peritectic temperature still we have liquid, but it is gamma plus liquid. This is the gamma plus liquid zone, two phase zone. So, solidifying is not yet complete. We have initially liquid, delta plus liquid, then gamma plus liquid, and then solidifying is complete at relatively lower temperature. So, you see the solidification range, temperature range is increasing as you are increasing the carbon. So, finally, it is complete at lower and lower temperature. Now, look at what is happening at a carbon concentration more than 0.5. At this composition, solidifying is through liquid to gamma, and then it is completely gamma. So, there is no trace of delta. So, that when it is less than 0.1, 100% delta. When the carbon concentration is more than 0.5, it is 100% gamma. In between 0.1 to 0.5, it is a mixture of, during solidifying it is a mixture of delta and gamma. Finally, everything is gamma, but during solidification for carbon concentration less than 0.1, it is 100% delta. Between 0.1 to 0.5, it is a mixture of delta and gamma. As you are increasing the carbon, it is becoming more and more gamma during solidifying, but when the carbon concentration is more than 0.5, say 0.6, 0.71, it is 100% gamma solidification. And look at what is the solidifying range, it is quite wide. Here it is relatively less. So, these you can make out that the solidifying temperatures are changing, actual solid dust temperature, this is the equilibrium solid dust temperature. With segregation, this will become still lower. So, it will become much more wider solidifying temperature range as you are going to high level of carbon. With more segregation, it is become more wider. So, now if you look at the role of steel chemistry in iron, plain carbon or low alloy steels. So, the solidifying mode, as I was telling you, can be three types: liquid to delta, or liquid to delta plus gamma, or liquid to gamma. That means 100% delta, 100% gamma. In between 0.1 to 0.5, it is a mixed mode, delta and gamma. And solidifying is completed at relatively lower and lower temperature as you are going to higher and higher carbon. So, now some investigators, they have devised one term called ferrite potential. That means what is the amount of ferrite when the solidifying is just complete. It depends on the chemistry. In iron carbon diagram I have shown it depends only on just carbon, but in steel, normal steels you do not have just carbon, you have other alloying elements like manganese, silicon, things like that. So, what is important is to understand the carbon equivalent. How the carbon equivalent is calculated? Look at here, is carbon plus what is the role of other alloying elements on carbon activity, it depends on that. So, manganese, then nitrogen, silicon, chromium, moly, titanium. Now, look at some of the manganese, it is plus, that means it increases the carbon activity. This is basically a like carbon forms austenite is austenitic stabilizer, manganese also austenitic stabilizer, nitrogen also austenitic stabilizers. So, these are plus. So, 0.04, 0.7, these are the factors which will indicate what are the relative effects of manganese and nitrogen on carbon equivalent. Look at other elements, silicon, chromium, moly, titanium, these are ferrite stabilizers. Okay. So, this will decrease the carbon equivalent unlike manganese and nitrogen. So, minus 0.14, minus 0.04, chromium 0.1. So, people have found out these figures after lot of experimentation. So, let us take this equation of carbon equivalent. There are other equations also, but this is most popular equation which is normally used for identifying the carbon equivalent with respect to solidification. There may be other carbon equivalent formula, but that is with respect to some other things. But let us talk about what is the carbon equivalent with respect to solidification. That means, when continuous casting is taking place, how the different alloying elements will affect the carbon equivalent. This is important because this carbon equivalent will determine, instead of just carbon equivalent will determine how the solidification will take place through delta, gamma or delta plus gamma. Where from this 0.5 is coming, basically is from this particular, this is 0.5. So, you look at this figure here. When solidification is taking place for any chemistry less than 0.1, any carbon less than 0.1% carbon, it is 100% delta. When solidification is taking place for any carbon which is more than 0.5, it is 100% gamma. In between, from the lever rule we can find out what are the relative portions of delta and gamma. As you are increasing carbon from 0.1 to 0.5, it is increasing from 0 to 100%. So, this relative portion has been basically shown in this figure. So, you just put any, say carbon equivalent is say 0.1, then what is going to happen? 0.5 minus 0.1 means 0.4 into 2.5 is basically 0. That means, as I was telling you, look at this figure, when you have 0.1% carbon, it is ferrite factor is basically 1, not 0, it is, I just made a mistake, it is 1, there is 100% ferrite. So, basically 0.5 minus 0.1 is 0.4 into 2.5, this is 1. So, when ferrite potential is 1 or more than 1, it is a delta solidification, or more than 1, it is delta solidification, say 0.05% carbon. So, 0.5 minus 0.05 basically means 0.45. So, 0.45 into 2.5 is more than 1. So, when ferrite potential is more than 1, this indicates it is delta solidification. That means, for any carbon or carbon equivalent less than 0.1, we have delta solidification mode. So, let us take a carbon equivalent of 0.5. So, what does it indicate? 0.5 minus 1.0. So, it is basically 0. If it is more than 0.5, so say 0.6, 0.5 minus 0.6 is minus 0.1. So, this is minus. So, when carbon equivalent is more than 0.5, ferrite potential is negative. So, that means it will indicate austenitic mode of solidification. So, I think it is clear, when ferrite potential is more than 1, that means for all carbon equivalent less than 0.1, we have delta mode of solidification. When carbon equivalent is more than 0.5, ferrite potential is negative, we have gamma mode of austenitic mode of solidification, and in between, that means ferrite potential is between 0 to 1, that means carbon equivalent is between 0.1 to 0.5, we have delta plus gamma mode of solidification. So, ferrite potential is an indication of chemistry. Simply, if I simply describe it, it is an indication of, it denotes chemistry in terms of the carbon equivalent of a particular grade for plain carbon or low alloy steel. So, if we know what are the alloying elements present, we can find out carbon equivalent, and if we know the carbon equivalent, from this figure or this relation we know how the solidification is taking place, whether through delta mode, whether through gamma mode, what is the relative proportion of delta gamma at the end of solidification, just at the end of solidification. Beyond that it will again change. Please try to look at this figure. This relative proportion is at the end of solidification, okay, here. Then as you are going to lower and lower temperature, it is changing, the relative proportion will change. It will no longer remain what it was at this peritectic temperature. So, after solidification also relatively, here everything always gamma is forming, here gamma is forming, but at this temperature is a combination of delta plus gamma. So, relatively delta gamma will change beyond solidification, but what we are talking is at this particular temperature, that means at the peritectic temperature, what is the situation at the end of solidification, what is the situation, that is what is important. So, I think you have understood what I mean by the role of steel chemistry, how it affects the mode of solidification, solidification sequence, whether to delta or gamma or a combined mode of delta plus gamma. This is very important to understand.